So for our first, call it, 10 plus missions, the reentry capsule is about a meter, in diameter, and can bring back about 40 to 50 kilograms of materials. There is a very wide set of basically pharmaceutical candidates that we can pursue that, 40 to 50 kilograms once a quarter far, outweighs basically, the total patient, population consumption, again, of the primary ingredient. Our pharmaceutical partners will take that primary ingredient, that crystal, structure that we have formed, and then go send that to a secondary CDMO manufacturing facility, where then that gets put into, a gel capsule, a tablet, a saline syringe, an IV drip, however that particular, basically drug, is administered to the patient. But that part does not have to happen in space.
Welcome to the Curiosity Podcast, where we go deep on a wide variety of technical topics with the smartest leaders in the world. I'm Immad and Raj, the co-founder and CEO of Merck.
And I'm Raj Suri. I'm the co-founder of Lima, Presto, and Lyft. And today we're talking to Delian, who is the co-founder of Varda, which is a space technology company doing lower Earth orbits and focusing on space manufacturing. And he's also a partner at Founders Fund and has done a lot of investing there as well. And he's kind of well known on X/Twitter as well. And I was really interested to talk to Delian. He's really well versed in his space, and very curious to learn about space manufacturing, which is a whole field that I had no idea about could make any sense at all. But actually, the way Delian explains it, it makes a ton of sense. Immad, what were you curious to learn about from Delian today?
Yeah, I think the interesting thing of his background in VC, kind of investing in aerospace and then becoming a founder here, gives him this kind of commercial mindset that's like kind of missing sometimes from these hard tech endeavors. And he's really thought about everything from first principles, like how do you do anything in space and how do you do kind of Varda in space. I am feeling like much more hopeful about all of space industry after speaking to Delian. I feel like, if there's enough smart people taking a crack at these things from different angles, we're going to have like a real space civilization in the next kind of 10, 20 years.
Absolutely. Yeah. And you definitely come away from hearing Delian and you feel a lot more hopeful because he's really thought about it from every aspect. He knows the technology inside out. He knows the customers, knows the use cases. He knows the economic model and the history of what's gone into this. So I think having people like that work on these types of problems is exactly what we need. And, and the ecosystem just gets better and better too. So very excited to talk to him today. And one recommendation for some folks is Delian speaks fast. So you may want to turn down the audio speed, so you can make sure you get every bit of wisdom he's spouting. So with that, let's welcome Delian.
Welcome, Delian. Thanks for joining us.
Thanks so much for having me. Excited to chat today.
Yeah, you have a really interesting kind of story, like software founder, kind of turned VC, turned to startup founder in the space tech. Can you walk us through how you ended up here and, what your kind of thinking was throughout it?
I've had this like long-term, fascination with aerospace, since a very young age. And originally was on this life path where, thought that, the sort of default path was going to be, study robotics and, computer science in high school, go off to, undergrad at a technical university, do grad school at Caltech, and then, join GPL and then join NASA to, do deep space robotic missions, given that, felt like the most, sort of applicable interest to, my skill set. And, call it like, freshman year of college, started to take a bit of a, sort of hard left turn and realized that, the world of, let's say, more academic training and working at a, sort of government, institution like NASA was less of an interest of mine. And, was more interested in the world of, sort of the speed of, Silicon Valley entrepreneurship there. And, when I looked, though, at, some of the heroes that I had, in the world of Silicon Valley, plus, call it aerospace, there was really only one common pattern amongst all of them, right? So if you look at, Elon Musk, Chamath Palihapitiya, Steve Jurvetson, et cetera, all of them basically, sort of made it big in normal tech and then went to go work on aerospace. And so, as I thought about my path forward, I thought, okay, I can do this, JPL thing. I can go be like an individual engineer. And I had a lot of friends from MIT that went and did that, go be an individual engineer, at SpaceX. Or I can try and follow the, Chamath, Elon, Steve, sort of path, and instead like go work in sort of like quote unquote normal tech, make it big there, and then basically go work, in space tech. And so, decided that sort of third path was, going to be my path. And so, decided to work, like you said, on, things that were in sort of pure software, become an investor. And part of why I actually ended up deciding to stick around in the world of investing, originally it was supposed to be just like a 1-year stopover, was because I, ended up within the first, sort of 6-9 months of working at Coastal Ventures, actually ended up sourcing an aerospace investment that we ultimately ended up making, Akash Systems. And through that, sort of had this like sudden aha moment. This would have been late 2017, early 2018 timeframe, after making that first investment, that rather than just having to wait until I was like, 40 or 45 and had made it big in normal tech and then, work on aerospace, there's a way for me to do it much sooner in a very strategic and interesting way that just wasn't just being an, IC, software engineer over at SpaceX. It was, the fact that because, people like Elon Musk had, sort of lowered the barriers of entry to the space, economy, let's say, now as an individual investor, you could actually, make investments even at, the ages of 23, 24 that I was, at Coastal Ventures, and start to, sort of work in the, space in a way that combines both technical expertise as well as, call it more business, sort of more business background. And so kind of got, hooked on this idea of, hey, let me, start working in aerospace today at 23, 24. If venture's the only way to do that today, great. Let me, sort of keep doubling down on that. And by the way, I kind of like being an investor a bit more than I like being a founder. And so let's just, sort of lean into this, and hopefully I can get back to the like building space companies, one day a bit later. And so, it turns out sort of paying that tuition for, 3, 4, 5 years, investing into space companies was a great way to sort of eventually prepare myself for the, founding of Varda. So, it had always been this like, let's say like lifelong interest, in how to, navigate my way towards building an aerospace company. But with a variety of sort of factors and, partially due to the advent of reusable rockets, rather than having to wait until I was, 60 to do something like that, I could actually do it, sort of much sooner in my career.
That's an interesting path. Would you recommend that path to kind of the younger Delian, or would you say that's like a pretty random set of things that came together and it would be hard to replicate?
I think today there are easier ways to accomplish this path, in that because the space economy has grown so much, like if your number one criteria is the same as mine, which is, build your own interesting space company, and you're, 19 and just dropped out of MIT, relative to, when I dropped out in 2013, there are a much wider set of very interesting early stage companies operating in the space economy. In 2013, it was effectively just like SpaceX, Rocket Lab, and Planet Labs. That was basically it. There's only 3 options. And at that point, all those companies were relatively scaled up. Your ability to join the founding team basically had already passed. If you look at it in the space economy, I can't actually think of an interesting space company that was founded between 2012 and maybe 15. Everything that was founded in that time frame was either too late, in that it was a rocket company that, wasn't able to then compete with SpaceX and Rocket Lab, or it was too early, in that it was, a fanciful idea that did not make sense before, the advent of reusable rockets. And so it was too early to its time. If you are, 19 and dropping out of MIT today, I think there's a much wider set of opportunities that you can join at the very early stages, not just be a cog in the machine, and also learn a lot about the, space economy, right? If I look now in the summer, fall of 2023, what are the interesting between seed and Series B aerospace companies? I can now name 10 of them versus, I think of the 2000, sort of 12 through 15 time frame, I think you could have really, named basically none. And so I think the alternative path today would just be go join an early stage aerospace company, use that experience, to, then, go build your own. So I think there's a much more direct path today. In some ways, I had to kind of sit on my hands for a bit to, wait for, the progress in the ecosystem, to catch up to the point where somebody with my experience could actually dive into it in a more interesting lens than just being an individual software engineer.
Yeah. You said you had 4 to 5 years experience on the VC side investing in aerospace and space companies. What would you say were the biggest kind of advantages of that? And do you think there's major kind of disadvantages from this kind of VC mindset you kind of came into this with?
Yeah, I mean, the advantages were, quite immense, in that relative to even hyper, sophisticated, SpaceX executives that had been at the company for 6+ years, my understanding of the end use cases, how to actually, sort of build up a business model in space, what the plethora of various, sort of vendors, regulators, et cetera, that you needed to interact with was actually much deeper, even with a much, smaller set of years of experience. Obviously now, did I have as many years of experience, like actually building spacecraft, going through the systems engineering of that, thinking through those trade-offs? No. But most of that stuff is not necessarily immediately the first, sort of relevant factor when, considering what business to build. So I think a ton of advantages there. I do think, obviously, there would be great disadvantages if I was the CEO of Varda with only the experience that I had, in that my ability to then assess, sort of top tier, mechanical systems, thermal engineers was effectively nil. But that was explicitly, something that I knew that I would not be great at and was looking to round out, with a co-founder. So I think the disadvantages were, I guess, pretty clear, but I don't think also impossible to solve for. And the advantages were definitely pretty, sort of immense. Not only understanding, how to analyze and understand a particular business model in space and what the end users are, but then also obviously like that skill being then helpful in relation to, describing the opportunity to investors for, financing.
Very interesting backstory. We'd just love to dive into Varda and ask some questions about why Varda? Why clearly the space ecosystem is exploding. Why did you pick this particular problem?
Yeah, the particular problem space that Varda exists within is something that I've been fascinated with since call it like 2009, 10. I think if you sort of study all of human history, when you look at any time that there's a permanent human settlement, outside of where the current sort of society is, the only time that those things ever become, sort of long-term sustainable end up being with economic incentives, right? Whether you have like the California gold rush, the original United States colonies, the Portuguese and the Chinese, naval empires in the 1400s, all of them, follow this familiar pattern where, when there is not a continuous economic incentive, things fall apart. When there is, things become very sustainable. And that's why, in the Apollo era, we effectively, visited the moon a handful of times and never went back because fundamentally there was no sort of economic use case for that. And, governments are only willing to throw empty dollars towards, sort of deep research and capabilities for so long. Ultimately, if they're not making a return on it, they themselves are not particularly efficient, but they are still ultimately capital allocators. And so when I thought about sort of the future of space, it was clear that there were people thinking about the early economic use cases around satellite communications, so obviously things like Starlink, the Earth observations, taking photos of the planet, like Planet Labs, ISI, et cetera. And while those initial economic use cases were interesting and definitely the right ones to pursue before reusable rockets, none of them really, had any justification for human presence at any level of scale, right? The moment that you're scaling up internet communication satellites, all you're going to want to do is just basically build more and more, parallel, individual, small, fully automated satellites. Same thing basically with, taking photos of the Earth. But industrialization of space, whether it's like asteroid mining, lunar ice mining, or in space manufacturing, all of those were business models where, fundamentally, autonomy was absolutely going to be relevant and almost certainly kick off the use case. But these were highly complex industrial processes that, if you observe those same processes on Earth, absolutely required pretty significant, human presence, even in the most automated, facilities. And so my idea was, when the time comes, focusing on the industrialization of space is ultimately what's going to create economic incentive for there to be, humans having extended presence in space. And that's how you eventually get to the point of having, a city the size of, San Francisco in low Earth orbit, and eventually a permanent lunar, base. So that was the original fascination, call it in 2009 through 11. In 2011, I actually, considered back in the day, originally potentially working with some of the very, sort of first generation companies working on some of these problems, but things like Planetary Resources, Moon Express, Made in Space. These were all, sort of Silicon Valley VC, sort of funded companies back in the day. But, ultimately felt like the time period was not yet, sort of correct in that all these are predicated on easier access to space, and that fundamental, sort of input had not been solved yet. And so as time progressed, and especially in the 2017 timeframe, where it was clear to me, if you basically study the curve of SpaceX's mass to orbit every single year, is almost a perfect exponential curve. And so it felt clear to me that sort of the access to space problem was going to be solved in a very short time frame. And so I did sort of a deeper dive into each of these use cases. And to me, it felt quite obvious that if you looked at everything from these, and again, probably top three being these, but many more between, call it lunar ice mining, asteroid mining, and in-space manufacturing, it felt very clear that the easiest one to commercialize in a very near-term time frame was in-space manufacturing. In some ways, just given the logistics and the ease of it. Like I love asteroid mining and lunar ice mining. It'd be very cool to get to work on those one day. But those are still, definitely pie in the sky relative to just staying very close to the Earth, manufacturing goods and bringing them back down. It's just like logistically a much, sort of simpler problem. Instead, it ultimately makes it, a much simpler business. So that was when you sort of, let's say, narrowed in from the broader industrial use case to, in-space manufacturing particularly. And then I really picked up the idea again after I joined Founders Fund in Q4 2019, where for the first time, a SpaceX rocket basically launched and landed, 4 times in a row. And it went from this like 2017 projection of an exponential curve to like 2019, very realistically, you were seeing this exponential curve, come to life. Paid a couple friends at SpaceX, that were involved in Falcon 9. And asked them, how much wear and tear are you guys seeing on these first rockets that are, landing? The resounding feedback was, these things are landing 3 or 4 times now. There's no reason why we shouldn't be able to get it to 20 plus times. And that's where the bit sort of, switched or flipped in my head, where it went from in-space manufacturing being something that I was like intrigued with to now this is no longer even like a theoretical future unit economics. Like today with these current reusable Falcon 9s, this is something that you can absolutely commercialize. And so I spent actually about 5 or 6 months, from the beginning of Q4 19 till basically, COVID hit, meeting with everybody that had ever thought about in-space manufacturing. Everything from the venture, backed groups that had, still stuck around since 2013, to, academics that had published papers, to, pharmaceutical researchers that were working within larger commercial corporations, but ultimately came away from that 6-month excursion and analysis, realizing that, nobody quite had the right approach. And the sort of, one-liner summary of it was that everybody that was working on this problem to date was only interested in working on this as long as basically they were working within the confines of the International Space Station and had backing and funding from NASA. And my first principle thesis, again, I don't know, a ton about spacecraft, but my first principle thesis was there's just no way that you're going to be like commercializing this type of business model on top of a like super bureaucratic, government-run, extremely low risk tolerance, space station. You should ideally be doing this, sort of on an independent, initially satellite, and eventually, sort of scaled up to what one would call, sort of a station. But when I talked to any of these groups that were working on this problem, all of them had no interest in ever, sort of moving off of the ISS, given that they, saw that there would be no funding from NASA. And they, didn't necessarily have interest in, figuring out basically one of their, biggest, risk factors or technical fears was, when you're a part of the International Space Station, you get a free ride down effectively from, the state, government or the national governments, whether it's the Russians with the Soyuz, the United States with the, Cargo Dragon and the Starliner. These things were, ways to bring back goods. You didn't really have to, pay for them. If you then went independent of the ISS, you were responsible for your own ride down. And so put the idea, sort of on the shelf again, but then finally really, decided to pursue it in summer 2020. And again, to tie it all together, it was basically this like super long-term fascination with ultimately, if you build this economic use case, this is ultimately what will lead there to be, eventually, 10 humans, 100 humans, 1,000 humans that are in low Earth orbit that are, generating economic value rather than just being paid for, by governments. And, finally decided that I just had to do it myself rather than, try and fund somebody else to do it.
Cool. Yeah. Makes sense. And tell me a little bit about this in-space manufacturing. So looking at the website, it looks like, there's some qualities in space that are different than Earth, which make it a different place to manufacture. Can you give us some like concrete examples of what is better or easier to manufacture in space than down here on Earth?
The simplest way to think about it in some ways is, there are 4 fundamental forces of physics. You have the strong and weak nuclear force, you have electromagnetism, and you have gravity. Down here on Earth, gravity is effectively just if it's constant, it's at what we consider to be 1g. It's somewhat arbitrary. The amount of acceleration that we feel on our surface is based off of the mass of the Earth, but it could easily sort of go up or down. It's very easy for us to experiment with, seeing what happens when gravity goes up. We do that, relatively all the time in a variety of material processes using either, pressure stirring or effectively like centrifuge systems. But at least on the surface of the Earth, for extended periods of time, there's no way to basically decrease, gravity. And so when you're up in low Earth orbit, what it gives you access to is effectively, you're not truly obviously escaping your gravity field, but you basically have a centrifugal force that is perfectly equal to Earth's gravitational force. So you effectively are in consistent free fall. And so you effectively experience the equivalent of, microgravity.
Well, by microgravity, like what fraction of 1g, I guess, would it be?
Typically, I believe microgravity is defined as micro, which is 10 to the negative 6th, right? So it's basically 6 zeros of 0.000001 g's. You never technically say zero gravity since it is effectively impossible anywhere in the universe to truly get to zero. But I mean, you can effectively think of it as zero gravity. but just the technical term is microgravity. And that type of, sort of environment being impossible to obviously, sort of create down here on the surface. And given that it's one of the four fundamental forces of physics, it has a wide, variety of effects. Some that are, cute in that, you can have the astronaut spinning around and playing his guitar and, have the water bubbles floating. Some that are, sort of more interesting and have, commercial applications. In particular, in what I would, categorize as basically like, mesoscopic chemical systems, which is called at the medium level of, scale. And I think the easiest way to, explain sort of why in these mesoscopic systems you end up having, gravity have a significant effect is actually just going to a very macroscopic analogy, which I like to use, which is a candle. If in front of the desks in front of us, you basically lit a candle. When you put your hand, above the candle, you're, taught as a kid, basically, you can feel that heat because the hot air is rising, right? Or hot air rises in a room. Why does that actually happen? What is the fundamental, basically, physics behind that? When you light the, wick of a candle, what's happening is basically you have a combustion reaction that is introducing thermal energy into the atmosphere around it. That atmosphere is comprised of, nitrogen, oxygen, et cetera. And so that thermal energy transfers into those, individual nitrogen, oxygen atoms, and basically takes that thermal energy, transfers it into kinetic energy. Those atmospheric, basically molecules start to move more quickly. When they start to move more quickly, and anytime you have molecules moving more quickly in a gas, it becomes a less dense gas. Anytime you're inside of a gravity field and you have that type of acceleration, you basically, have, sedimentation effectively, or, convection that occurs where effectively the less dense gas moves to the top of the room and the more dense gas moves down. The same thing is true with liquids as well, right? So the reason that, the hot air rises from a candle is the same reason why inside of a glass of water, ice, floats to the top of the glass. Basically exact same reasoning. So as that heat basically moves up, basically you create negative pressure in that air pressure system. You basically have these, constant, currents forming. If we take that same basically candle and you light it inside of a microgravity environment where there's enough oxygen to sustain the, reaction, et cetera, what ends up happening? So you still have the combustion reaction, right? The wick still lights, ignites with the oxygen around it and consumes it. It still creates that thermal energy. That atmosphere again speeds up. It becomes less dense, but now you're not inside of a gravitational field. And so what ends up happening with that less dense gas? It doesn't move around. Instead, it just very steadily disperses its kinetic energy throughout the entire room, very slowly through, what's known as a basically diffusive, motion. So that's a very macroscopic analogy, but let's take it down to the microscopic level. If you're thinking about, sort of trying to get, sort of two molecules to attach to one another. If you remember from high school, the sort of, very simple molecular reaction is, take two molecules, put them on top of a Bunsen burner. You're basically trying to get above that activation energy, so that you eventually get into a different, sort of potential state, right? And anytime that you're, sort of trying to do that on Earth, and especially if you have two things that are slightly different molecular weights, those same basically convective, currents end up, effectively dominating where, one of those molecules may end up being, heavier versus lighter. You start to apply thermal energy into the system. It basically, starts to, move those things around with convective currents. And it makes it much more difficult to basically, especially if there are, let's say like multiple, sort of energy states that the, reaction can land in, it's very difficult to precisely control which one because you have a lot of this like entropy or let's say chaos in those chemical reactions. Take that, sort of same reaction up to the, microgravity environment to space. Much easier to basically introduce thermal energy without basically having these convective currents. Instead, that thermal energy steadily diffuses. You can precisely basically control that molecular reaction. Okay, so we've gone from candle analogy to microscopic, sort of, chemical system to, okay, well, what does this actually mean, in the world of like economics and, capitalism? Why does this, fucking matter at all? By far, sort of the, gold standard, let's say from the International Space Station or, the best, case study was performed by Merck. They're one of the top 20 biopharmaceutical companies in the world. They took their blockbuster monoclonal antibody biologic. It's basically like a cancer drug. It's called Keytruda. It does about $25 billion a year revenue, for them. So, it's a massive drug. But anyways, they took it up to the International Space Station and to provide a very simple analogy for how this pharmaceutical is manufactured, you can effectively think of it as on the ground. Think of it as almost like a saline solution where you're trying to evaporate things out and little salts are basically like left behind. And what happens when they manufacture it on the ground is as each individual, what is known as a nucleation point forms, basically where a crystal forms for the first time. What ends up happening is because you have those convective currents, more basically salt water ends up attaching to each individual like nucleation or crystallization point and makes it so that each individual crystal ends up being basically very variable in size because you have these convective currents, basically moving, the solution around and making it so that these nucleation points, rather than being very uniform, can be sort of a wide range of crystal sizes. So because this is a drug where you try to distribute it to patients and those crystals end up breaking down in your blood very differently depending on the size. Basically, the smaller that the crystal is, the more easily it breaks down in your blood. The larger that it is, the more slowly it breaks down in your blood. The way that they end up basically delivering this to patients is effectively having you come into a clinic and do like a 1 to 4 hour basically intravenous drip. On the International Space Station, effectively what they were able to confirm is when they basically took that same process, because again, there weren't those convective currents, you didn't have solution moving into each nucleation or crystallization point. Instead, you basically had like thousands of individual nucleation points that were all perfectly uniform, because basically the little salt crystal would form. There wouldn't be new solution that would flow towards it because you didn't have convective currents. And so what does that mean as a patient? Well, now you know that every single crystal is basically, it's a very narrow monomodal basically distribution. And so that means you can perfectly predict how it's going to break down in the patient's blood. And so instead of having them come into a clinic for 1 to 4 hours every single day, you could instead just send them home with a series of syringes or subcutaneous injections they can take from home. So this $25 billion a year drug, basically, rather than being distributed to millions of patients, in a IV clinic, for hours and hours every single day, instead now has a form where they can basically send patients at home. And when you think about the actual dosing, a Varda capsule that we bring back with 40 kilograms, this type of material, can dose a very significant patient population, far in excess of cost it takes to launch it to orbit, manufacture, and bring it back down. So that would by far be the blockbuster use case that we would love to sort of work on. But there's a wide set of other ones where you can basically think of this microgravity physical effect as just changing the performance characteristics of a drug, not in relation to like what disease does it cure, that it does not get affected by microgravity, but you can think of it more as like what is the crystal structure or the crystal form, and that typically can affect everything from like the shelf stability, whether it's room temperature stable, whether or not it can pass the blood-brain barrier, how easily it breaks apart in a patient's blood. And a lot of times those could be some of the sort of critical or limiting steps of actually bringing a drug to market. So anyways, long-winded, answer to your question, but tried to start from first principles and work all the way through to commercialization.
Did you do a full kind of TAM analysis of like all the drugs this could be applied to, and like what would be the TAM if you did this, or it's just too hard to kind of figure out?
I never believed that much in TAM analyses for any investment that I make, and so it didn't feel that relevant for a company that I'm starting. In that, look, the sort of one-liner TAM analysis was we have a monopoly on one of the 4 fundamental forces of physics in an area where chemistry is extremely important to be precise. And this is, an extremely, large market, far bigger than anything that anybody in the tech industry basically works on. And so it didn't seem to warrant a super precise analysis, especially because as rocket, launch costs continue to decrease, as our cadence continues to increases, the economics change not by like 10, 20%, but change by orders of magnitude. And so therefore the TAM you can even tackle also changes by, order of magnitude, given that it's a question of economics and, sort of value, creation. There's definitely drugs, the example that I like to provide, by the way, that, sometimes helps people understand, why does crystal structure matter? And if you take, ibuprofen, you've almost certainly seen basically, 2 types of ibuprofen whenever you go into a pharmacy, where you have basically like the long-lasting ibuprofen that is used for things like, arthritis. And then you have the short-acting, ibuprofen that is effectively, meant for like a headache. It's still ibuprofen. It's still the same molecule, but the difference is basically one of those molecules is being put inside of a crystalline structure that breaks apart very slowly in your blood, so that arthritis, you have something that basically like lasts 12 hours, but at a very low level or low dosing. And the other one is the exact opposite. It's basically meant to break apart very quickly in your blood and dose you very quickly, so you basically reduce the inflammation in your headache or whatever like injury that you have. And so I'm not saying that we're going to be working on ibuprofen anytime soon, but as you start to basically make the economics of manufacturing in space cheaper and cheaper, you can start to go after things that are less critical, let's say in terms of value proposition, where maybe one thing was that, oh my God, we can't bring this drug to market because it needs to pass the blood-brain barrier. Space manufacturing is the only way to bring this like neurological compound to market that is like extremely high value. And over time, it might be like, hey, like when we make it on the ground, it's like room temperature, or it's like, shelf stable at like 2 degrees Celsius. So like we kind of need a cold chain that's pretty annoying. And then like, patients have to put it in their fridge when they get home. But if we make it in space, it's like room temperature stable. And so it's like, that's more marginal, but it actually may end up being cheaper over time, to actually just, solve it in space rather than actually, have a cold chain down here on the ground.
So when Merck, like I guess working with someone else, did this test on ISS, like I guess how long ago was that, and why didn't like that group try to commercialize it, or was ISS really like holding them back?
Merck mostly, ran with it, on their own, and they did this in late 2018 and published the results basically like Q1 2019. So it was, again, one of these things in the 2019 timeframe. As I was considering the idea, it was definitely a heavyweight where it went from sort of a lot of interesting sort of theory, tons of great academic experiments. Like this was just true, like in my opinion, sort of blockbuster commercial results. Ultimately, there was no path forward. Merck didn't have a company, to go work with or partner with to figure out how to scale this up. It's not like they could go to NASA and say, hey, please shut down the International Space Station. Instead, allow us to take this over and turn it into a drug manufacturing facility. There was no commercial player at the time that had, let's say, any path forward in terms of, allowing them to work off of the ISS. But I can't comment, let's say, on our discussions with various, sort of pharmaceutical partners. But what I can say is the primary principal investigator of that experiment by Merck, the blockbuster result, did provide a public quote for our launch article that was done by CNN. And in it, he basically explicitly called out, the ISS has been a phenomenal place for us to do, early, research and validation work. But I find, a platform like Varda that allows us to do this at greater scale, lower cost, and higher cadence. Extremely intriguing, and I look forward. I think he said something along the lines of like, I look forward to partnering with them, even if we haven't quite yet today. And so, clearly, this sort of value proposition is resonating with the groups that had by far the best results from microgravity.
So, when you're making these new crystal structures up in lower orbit space, and you bring them back to Earth, there's no like disruption to the structure and changing the gravity environment, or is it just the way that it's formed that stays permanent in different gravity environments?
Think of this as basically like a phase transition where you basically are taking something that was previously a liquid and basically turning it into a solid. Once it has its solid state form, it then maintains that solid state form, even if you put it into a different gravitational field. What mattered was what was basically the acceleration that it was experiencing during the phase transition. So from the transition from liquid to solid, it matters a lot what acceleration is. After it's solid, it maintains its crystal lattice. Now, that is a not entirely perfect answer in that reentry, not anything here on the ground per se, but the reentry process, does put significant G forces in our current reentry capsule. So we rip anywhere from like 8 to 11 Gs during reentry. There are certain molecules that the solid state forms effectively aren't stable at that level of acceleration and shock, and so they will lose that structure that you formed in space. But we basically have started out by focusing on what are prototypically considered small molecules. Small molecules are basically what all drugs were until, call it like the 2008, 2009 timeframe. Everything from like ibuprofen to basically most drugs on the market were small molecules. In the 2008 through 9 timeframe, basically they started working on what are known as larger molecules or biologics. Basically, think of it, rather than being formed through orgochemistry, mixing chemicals together and heating and cooling them and creating various chemical reactions. Instead, these things are formed with closer to biological processes. Think like something that either looks like yeast fermentation, or eventually even ultimately up to something closer to what looks like a human cell. Those type of things for sure are more sensitive to G forces, and so we won't be able to tackle that type of product today. We would have to improve upon our reentry vehicle capabilities, where it can more precisely control G forces by basically having active aerodynamic controls. So across all these drug categories, once you create that solid state form down here on the ground, totally fine to sustain it. It's actually more the process of reentry itself, less so being down here on the ground that affects it.
You mentioned reentry a couple of times. It's kind of interesting. Like, I feel like space manufacturing should not have to solve the reentry problem. It feels like someone else would have solved that. But is it a really hard problem? Like, are you just hitting things against the Earth's atmosphere? Like, how do you kind of go around thinking about reentry?
Yeah, I mean, in some ways, when I was considering starting the company, I fundamentally realized that the space manufacturing problem is a reentry problem, that was the fundamental, sort of limiter in a lot of ways. The actual space manufacturing portion of it, if you look at what we're doing to these various pharmaceutical compounds, it's complex for sure. It's not a sort of trivial problem, but it's clearly been demonstrated it's possible to be done on the International Space Station. People are definitely mixing together complex fluids. They're recreating some of the industrial processes that are done here on Earth, in a microgravity environment. So like one of the simple examples is like when you mix fluids, sometimes down here on Earth, you rely on gravity to basically bring them into a beaker and you stir them around. Up there, you have to rely more on like microfluidics and capillary action and things like that. But point being that is like difficult engineering, but not anything too crazy. But the reentry problem, and especially doing that at sort of high cadence, was just not something that anybody had really done. Because if you think about it, why come back from space? Like there's just not any particular, reason to. The only time that we've really come back from space on a consistent basis is to bring the humans back. Because humans do want to eventually return to their life, down here on Earth. But other than that, there's nothing to bring back from there. If you, are communicating with your satellites, you communicate via radio. The satellites themselves, it's easier to just let them burn up and send up a new one than try and bring it back down. And so there really hasn't been any non-government use case for bringing things back. The only times where small scale reentry capsules like Varda's have really been landed are two things. One, in the more recent years, including almost exactly 24 hours ago, asteroid sample return missions, where NASA, for example, yesterday landed in the Utah desert with this mission called OSIRIS-REx, where they basically went out to an asteroid called Bennu. They launched in, I want to say 2017, landed at Bennu in 2019, and then I think basically left Bennu in late 2020 to come back to Earth. There you are trying to explicitly bring something back from space. It's a small asteroid sample, and the Japanese did it twice with Hayabusa, and also NASA did it once with Stardust in 2004. But anyways, other than these asteroid sample returns missions, the only other time that we really did reentry capsules small scale that didn't have humans on board regularly was actually in the early days at the same time as the Apollo program was going. But there was a parallel program going that had almost basically as large of a budget as the Apollo program and just as much headcount called the Corona spy satellite program, where basically in the very early days before we had powerful enough radios to communicate with satellites and be able to actually downlink photos, we would actually send satellites up to space to take photos of the Soviet Union. We'd take photos on physical Kodak film, reel that film into basically small reentry capsules, and then re-enter those reentry capsules and actually pick them up with basically military bombers and actually use a skyhook to pick the parachute up basically out of the air once the reentry capsule is down on the ground. And we flew about, I believe, it was 134 of those Corona reentry capsules, and I believe something like 120 of them were recovered. So they had a really high success rate. So clearly it was possible to solve this reentry problem. Humanity had obviously, done it, about 50 years prior. But in the past 20 years, really nobody had solved a reentry problem. Is it a difficult problem? Absolutely. There's a reason why, the United States has yet to field an operational hypersonic boost glide, interceptor or, weapon system, from space, and that it is effectively, a system that would be trying to reenter. It's just an extremely complex environment. Getting to space is definitely hard, but maybe coming back from space is even harder, because when you're getting to space, really the rocket, what it's doing is it's basically going up and then it's going sideways super, super fast. And in order to come back from space, you could do two things. You could send a fully fueled Falcon 9 all the way to space, somehow get it up there and just use that to slow you down. Or you can take the cheaper way coming back and instead just hit the atmosphere and basically use the atmosphere to slow you down. But when you're up there, you're basically going Mach 25. And so Mach 25, hitting the atmosphere at those speeds introduces some pretty complex factors. There's basically three main things that you get hit with. One is effectively G forces or shock forces. So if you've ever been on a commercial 747 flight, you hit a little pocket of gravity. It absolutely obviously creates some level of G forces. Imagine that, but obviously at Mach 25, those G forces are far more intense. Two, there's a thermal load. If you ever watch the Tom Hanks, Apollo, film, he's coming back through reentry. There's all that, basically plasma around him and, basically that heat. You get to higher than the temperature of the sun on the actual, capsule's heat shield. And then the third is because you're going so fast, you're actually separating the individual atoms in the atmosphere from one another. So if you have paired together nitrogen or oxygen, you're actually creating highly charged ions that actually form the fourth state of matter. So rather than being a liquid, a solid, or a gas, you actually form a plasma. And plasma also interacts with aerodynamic vehicles in very sort of difficult to predict ways. And so the combination of all of those three factors makes the reentry environment an incredibly difficult environment to engineer for. And so when we thought about, Varda, especially in the early days, we fundamentally thought about it in some ways as solve the reentry problem first, because if you prove to everybody that you can reenter on a regular basis, then the in-space manufacturing is sort of a walk in the park in comparison.
Have you proven that? Have you done a test reentry?
We, had our first launch June 12th of this year. And then, we did have some planned dates in both July and September to reenter. But, unfortunately, are still working through some government partner, let's say, collaborations in order to, have the approval to land, hopefully relatively soon. So the vehicle's ready to land and ready to do the test. But unfortunately, in the United States, it's not as simple as that in order to bring a reentry capsule back.
Yeah, I'm very excited. So when you talk about doing the space manufacturing, I'm wondering about other meaning of the word space. How much actually area do you need to do this manufacturing, and how will it actually scale? At some point, are you gonna have a full factory up there, and you plan to do it all automated, so there's no humans. You're doing like a basically fully human-free flight, right?
Yeah, we'll definitely be automated, for now. But referencing, if you remember my very first, answer around why work on Varda, it's because there is eventually that motivation, to have humans on there. Even if you look at the most automated pharmaceutical or semiconductor manufacturing facilities on the ground today, they do on some occasional basis do require human maintenance. And so I do think there will be a tipping point for Varda where today it absolutely does not make sense for economics to have humans up there. But over time, as you get to a large enough basically manufacturing facility, you will have justification for humans up there. And that's how you get from 1 human to 10 humans to, hundreds of humans. When you think about how much space that we need, especially for some of the early, sort of pharmaceutical drug candidates that we're working on, people underappreciate, how much of an actual, drug they're taking when they, come in to, take something. If you look at the Pfizer COVID vaccine, entire United States consumption in 2021, 2022, which was, I believe, on the order of about 600, million doses. If you look at the actual like active pharmaceutical ingredients, the thing that is, actively, interacting with your body, which is the thing that Varda works on, that primary ingredient for all of those 600 million doses in the United States effectively filled up only 2 milk gallon jugs. Now, the 2 milk gallon jugs of like mRNA crystals then get distributed out into like, hundreds of millions of individual doses so that when you go in, you have this like saline syringe, at the, clinic where you got your, COVID vaccine. But it only has a very, very small amount of that, sort of RNA crystal. And that secondary manufacturing process in terms of putting into putting the primary ingredient into a saline syringe, that for Varda still happens on the ground. We just basically focus on those like 2 milk gallon jugs. So for our first, call it, 10 plus missions, the reentry capsule is about 1 meter, in diameter, and can bring back about 40 to 50 kilograms of materials. There is a very wide set of basically like, pharmaceutical candidates that we can pursue that, 40 to 50 kilograms once a quarter far, outweighs basically, the total patient, population consumption, again, of the primary ingredient. Our pharmaceutical partners will take that primary ingredient, that crystal structure that we have formed, and then go send that to a secondary CDMO manufacturing facility, where then that gets put into a gel capsule, a tablet, a saline syringe, an IV drip, however that particular basically drug is administered to the patient. But that part does not have to happen in space. So yes, for sure, obviously over time, we will need to, get larger, but there's no reason why, at our current scale, we couldn't make this into a, sort of multi-billion-dollar company regularly bringing, drugs to market. Obviously, I, fantasize about the day when I get to send up, something that is like the size of a skyscraper up into space and have that, sort of manufacturing. But that is not, a requirement for Varda to, IPO anytime soon.
I'm just wondering what do you think the requirement is for Varda to, get to a decent scale?
I think Varda could be a multi-billion-dollar company, flying, 6 to 7 missions a year of like, 300 kilogram satellites, basically. I don't think we need to go, larger than that in order to, hit that. If you look at, some of the drug candidates that, we're working on with pharmaceutical partners, the dosing on a per patient basis does not require something that is a permanent, station or, anything much larger than what we're, sort of developing today. Think about, sort of Varda's business model or provide a, parallel, with the way that we end up partnering with our pharmaceutical clients and the actual contract structure looks very net similar to groups like, if you're familiar with like Ginkgo Bioworks, AbCellera, Halozyme, where effectively we partner with our pharmaceutical partners on the particular drugs that they're working on that have crystal structure, basically issues. And we get a combination of both milestone payments based off of the actual, deliverables that we bring to them, but as well as effectively, you can think of it as like, royalties in the actual or equities, basically in the drug that we work on, that when it, gets brought to market, we, become a partner in the actual, drug. And so, I don't think you'll see us working on anything, sort of much, much larger than what we're working on today in the next 3, 4, or 5 years. But for sure, over time, after this company's, much larger than it is today, definitely look forward to kicking off the V2 and the V3 that will all steadily get larger and larger. But for now, I would say it's more, higher cadence of our current, sized infrastructure and really improve the economics of that. And that will be more than, plenty to, get us through to being a public company.
Got it. So the order of operations, if I can just summarize, is like, nailing what you're currently doing, the 300 kilograms, sort of loads, payloads, and you're trying to get higher cadence of that, improve the economics. Where are you on the economics? I mean, if you can give us our range, like where do you need to be versus where you are today?
Yeah. In this current V1 architecture, you can basically think of like our all-in cost for our very first mission that we did, about like $12 million, a pop. There's no reason why by like mission 4 or 5 or so we'll be able to get that down to like 5 or 6 million. And what we're really ultimately aiming for is by mission 10. There's no reason why, basically, with a bit of reusability, why we shouldn't be able to basically get this down to like sub $2.5 million a mission. At that price point, with the amount of pharmaceuticals that we're manufacturing, at that point, we'd be far more focused on like basically scale up of that 2.5 million emission, more so than actually continuing to improve the economics. And all of that is basically like assuming that launch costs basically stay flat, where they are today. So yeah, that's the sort of cost curve that we're looking to ride down. Obviously, we're still in our first mission, so we're still on like the most expensive parts of that sort of cost curve. But thankfully, beyond just the pharmaceutical business that we've been talking about, we also have a ton of support from the DoD to utilize our capsules effectively as a hypersonic testing mechanism. So that also offsets a lot of the like upfront R&D and NRE, and also establishes, let's say, like a base cadence of the number of flights that we do every single year. So it makes it so each marginal pharmaceutical flight is sort of much cheaper, and we can get to that scale that gets us to that sort of cost structure much more easily than if we were to just rely on the pharmaceutical business alone.
That's fascinating. So the DoD is helping you with these startup costs.
100%. Varda would not exist if not for the DoD.
It's kind of interesting the way you describe it, especially with the 2 milk gallon jugs, which is like a really interesting data point. It seems like, the dollars per kilogram of pharmaceutical kind of, I guess, end product is just super duper high, right? Like there's probably nothing else like it. I guess outside pharma, is there something else that it does have this kind of extreme high dollar per kilogram of manufacturing kind of output that you think is viable in space manufacturing?
Other than illicit drugs, there's basically nothing on Earth that sells for more than $100 a kilo, other than basically biopharmaceuticals. So,
well, illicit drugs are also a pharma product.
Yeah, exactly. And even then, there's only a very small handful of extremely high purity illicit drugs that even sell for that amount per kilo. So that was sort of the realization that we came to relatively quickly, was as we were looking at basically like value generation, where we could, sort of attack various markets. There's been a ton of interesting work around fiber optics, semiconductors, in space. But at the end of the day, you get stuck with just this mass problem. Like, as much as like the A5 chip in your phone, and the iPhone is, very valuable and very light, it just still pales in comparison to drugs. It's just like orders and orders of magnitude, sort of difference. And so, it's just a lot easier to deal with the economics of space when you're talking about, okay, $5,000 a kilogram launch cost, which, end up meaning, okay, your total, cost of emission all baked in are like, 25, 30, 40,000. Because obviously, you don't want launch costs to, represent, too small or too large of a portion of your total, sort of flight costs. And it's just a lot easier to work with, compounds that are $1 million a kilo or, $500,000 a kilo than it is to work with something that's, far less than that.
Yeah, that's interesting. What is position number 2? Is it fiber optics or is it semiconductors or something else?
I think it's such a steep drop off that like in some ways nobody knows. And it is interesting because there's like this whole group at like Stanford that is like extremely obsessed with, semiconductors in space. They like try to invite me as a speaker. And I basically told them, well, I was like, I'm going to tell you that I don't think this is a good idea. So I don't think you like want me as a speaker. And so they basically like hung up on me and I was like, okay, I don't know what you want from me. And then there is like this, like, there are some like, smaller startup, companies actually like trying to focus on this, but yeah, I just like have a really hard time. Like if you look at it, actually, like our chief science officer, that now obviously, entirely works in pharmaceuticals. He came from the semiconductor industry. Like, we're like pretty deeply familiar. We definitely like studied it, quite extensively of just like, is there something that we could do here? But it's just, I'm not saying that there isn't value to be had. It's just like, you're never going to, build a business with good unit economics on it in the next decade, 2030 and beyond, Starship's online, lunar base, whatever, all bets are off then. Cause now you might be talking about like, $25, $50, $100 a kilogram. Sure. Then there's going to be a ton of stuff. I mean, but then at that point, you're also talking about like people are going to like start brewing wine in space just for the novelty of it. Right. So,
yeah.
I can see people paying a lot of money for that, like wine.
Yeah, I would pay for space wine.
There's this like bottle of space wine that's sold for, I don't know, $100,000, something like that. So it's like, it exists.
Maybe a space engagement ring, like something that's just like expensive for the point of it.
Space rocks.
I once heard someone say like it might be interesting to like 3D print like hearts in space. Is that a real viable type thing, or was that just like some like sci-fi talk?
I think that's one that is more likely we like solve it terrestrially. I'm not saying it's like totally impossible, but it's just like a pretty difficult problem in that if you remember we were talking about basically like stability, g-forces, loading, etc. during reentry. Reentry is not that kind on a heart that's inside a human, let alone one that's outside of a human. So I think a little bit of a trickier problem. So it is something that like NASA's been investing a lot into. They like recently did this release about talking about like somebody building like a like 3D printed like meniscus up in space. But while we're interested in biopharmaceuticals and the sort of healthcare industry, I think the like organ and tissue printing space is going to be a tougher one as well.
What's meniscus?
It's like a ligament inside of your knee, and so they basically like 3D printed a ligament in space.
Oh, that's interesting. I guess less constraints on like what G forces it can take. Maybe.
Yeah, exactly. It's like an easier problem than a heart. A heart is a very hard problem to solve. Ligament is a step along the way. Let's say
lower stakes too.
Yeah, lower stakes.
So when do we get to a level where like you need humans in space to run this manufacturing? It seems like the tendency is probably to try to automate as much of it as possible, right?
Yeah, I'm not claiming that it's in any sort of short time frame, but if you look at the set of companies that are out on the market today commercializing various use cases, I think Varda will be the first to have an economic use case, sort of for it. If I were to try and put a prediction, I would say it's like no earlier than 2029, no later than 2035, for Varda to justify that. But in relation to the improvement to our economics, you basically start to want to invest into reusability. The first thing that's very easy to reuse is the actual reentry capsule. That thing literally comes back down on the ground. You can analyze it. You can see basically what it takes to refurbish, start to engineer around basically making it sort of reusable. The second step is the actual basically satellite and manufacturing portion of the satellite. That right now we basically burn up after each orbit. But instead, what you could eventually imagine doing is instead actually leaving that as a somewhat more fixed station in orbit, and instead bringing reentry capsules basically with raw goods to the manufacturing station, exchanging it for fabricated pharmaceuticals, and basically bringing it back down. Initially, I think what you'll see is basically just like similar to how Starlink has a constellation of 1,000 satellites, you might see a constellation of Varda satellites that are a bit larger. Maybe they're 1,000 kilograms a piece. And one of them is small molecule focused. One of them is biologics focused. One of them is dealt with more toxic compounds. One has more, thermal processes and super high temperatures, right? And so you'll see like a constellation, and basically depending on which manufacturing process your drug is most suitable for, you'll get, sent to that one. And initially those will probably be distributed. But once you start to get to on the order of like, sort of several thousand kilograms on each of these, it will start to make sense to aggregate them. And then basically, likely initially just have like a human visitor that comes by, maybe like, 1 week every, 3 months or something like that, does a bunch of like, manual repairs and things like that, given that, yes, automation is, really, phenomenal. And I think we're getting better and better at robotics down here on the ground, but there is still some level of like fine motor control that, humans can have in decision-making that you can't yet replicate. And I don't think you will be able to, anytime soon. And so I think that's what it probably looks like, is like we like start to pay for like a Crew Dragon to, bring somebody close to our station, do a, sort of spacewalk. And then once you're doing that, like rather than 1 week every 3 months, you do it 1 week a month. And then it's like, 2 weeks a month. And then all of a sudden it turns out that somebody just needs to live close by. And so then they actually like hook into our station for water and for oxygen and things like that. And then all of a sudden you have like one human living there. And I think, that stuff is probably called 2028, 2029 timeframe at the soonest. That would be sort of the best possible trajectory, for Varda. Definitely, a lot of work in order to make that happen.
So initially you're not reusing the factory? Like, did I hear you correctly that you're shipping the raw materials?
Yeah, everything is one-time use today. Basically, we burn up the whole basically satellite and factory and everything after each use. Just make it as simple as possible, because the docking and rendezvous problem of making it so you can reuse the satellite and you can bring new reentry capsules to it is like $100 million engineering problem. And so easier to not tackle that today and instead just do basically disposable. Just like, Elon with Falcon, 1 in the early days of Falcon 9, it was fully disposable end to end. Same thing here, just keep it simple, disposable end to end, prove it out, and then start to focus on reusability.
Yeah. It's kind of funny on the ground, everything is reusable by default.
Yes.
And in spaces, everything is
not reusable by default. It burns up when it hits the atmosphere, except for reentry capsules. Those don't burn up.
What are the timelines towards this cost curve you talked about? I think 12 million down to like 2. Is that like 2029 as well, to 2035?
Oh, no. That cost curve is much, shorter. We'll have it down to like 2 or 3, million a launch by like 2025. So yeah, that's a pretty short time frame.
And the main levers there are the reusability. Is that the main lever to get it from 12 to?
The main lever is, primarily, there was a set of, components and things that we bought off the shelf to get us up to flight basically as quickly as possible that are over-engineered for our mission. But we preferred to purchase them, 1, because of speed to flight, because we could buy something off the shelf, and 2, better to over-engineer the first handful of missions, get data sets about what the actual environment looks like, what it's experiencing, and then you can engineer basically, around that actual, flight data. And so by 2025, you'll notice that basically like our satellites start to look much less capable, basically, as we just focus on the minimum level of capability rather than, the first handful of satellites being, sort of over-engineered to ensure basically, success. That cost curve is a relatively short-term cost curve.
Right. So, and you say your first launch this year was June 12th, right?
Yeah, June 12th at 3:10 PST.
Yeah. So, and you started the company in 2020, right?
Technically, yeah, I met my co-founder August 2020, incorporated November 19th, 2020, but we didn't really open our office doors until January 19th, 2021. So, when you look at like, a significant number of people working on it full time is really, let's say, Jan 2021.
Wow. So still 2.5 years to our first launch. I mean, that's pretty incredible, isn't it? Like for a space company to do that seems like a very short period.
Yeah. Credit to my co-founder. Sort of core cultural value of Varda was, the trains take off on time. Even if they don't have all the features that you want, even if it's a little bit riskier than you want, at the end of the day, the trains take off on time. And so I think it's that iterative hardware, sort of approach and obsession with schedule that's, led to our ability to, sort of get to flight so quickly. And in some ways, just the maturity of the space ecosystem relative to a decade ago. There's just a set of components that we were able to buy off the shelf that groups like SpaceX were not able to in 2008 that made their life, sort of far more difficult. And so, I'm very proud of the fact that, we were able to get to flight, so quickly. And for sure, we want to, continue to improve, from our first flight. Definitely, things that we learned about the satellite and, about the mission already that we definitely want to fix by the second and the third and the fourth. But better to learn those and get to flight more quickly rather than like, I think a lot of companies just get stuck in this like engineering analysis paralysis state, constantly trying to improve upon the satellite before they ever actually fly it. But it turns out the best way to learn about your designs is just go fly them.
Yeah. Cool. I mean, I know the software companies that don't launch in 2.5 years, let alone space companies. What do you think the future of the space industry looks like? Like 10 years from now, what do you think we're going to be talking about that's already real? Like 10 years ago, like things like Starlink weren't real and like, it sounded like science fiction and reusable rockets weren't real. What do you think 10 years from now will be like, yeah, this is normal?
I think you'll have, north of 100 humans in orbit, on a permanent basis, call it that being the minimum number. And, maybe that's stretching up to, 1,500 or maybe even 2,000. So, sort of small village in low Earth orbit being, quite, sustained. And I think, call it, the number of people that we basically have on the ISS today, call it between 9 to 17, being a part of a lunar base. And I think, both those things will feel, extremely normal, just like the International Space Station has been permanently manned, since, 1999, 24/7. I think, call it in the 2028 timeframe or, 2032 timeframe, you'll basically have the initial, built out, lunar base that, from then on will be, permanently manned. And again, those types of things, they're going to be government run to start, just like the ISS basically proved out the early days of low Earth orbit economy by, being subsidized by the federal government. The same thing will be true for the lunar base. Groups like Varda and, Axiom Space and, VAST will take over basically low Earth orbit because you no longer need federal incentives to build there. That'll just be something that is done by commercial entities. And, sort of NASA and the federal government will take over the, sort of next, next frontier. And I think, lunar sort of surface will absolutely be that. And so I think that will feel very, very normal, as well as, I think people have talked fancifully, obviously, about Mars for an extended period of time, but there's not been any type of concrete, it's not like nobody's designing a vehicle that is currently, going to Mars with humans on it, right? Like that is something that people talk about in theory as a future thing that humanity might want to do, but nothing is currently being worked on. I think 10 years from today, just as we see that today people are designing things to go to the moon, in 2032, you will see things that are actually being designed to go to Mars.
As you said, right, the key thing is the economic incentive. So we need to figure out that piece of it for Mars.
Yeah, that one I think for sure will be a little bit harder to figure out relative to low Earth orbit and the moon. But I think if you have really established, trading posts, let's say, on in low Earth orbit and the moon, the moon to Mars problem, in my opinion, is a significantly easier problem than the Earth to Mars problem. In that if you have established basically trading posts in low Earth orbit and the moon, it means at that point you have a functioning society that has likely significant capabilities. Like if you look at the International Space Station, they have a robot arm, they have humans up there, they for sure have microscopes and a decent amount of lab equipment, but that's about it. They don't have bulldozers, they don't have raw materials, they don't have the ability to create large scale structures. If you have a lunar base, you're talking about the idea of something that, is obviously permanently, settled, is built, And you're likely talking about industrial equipment that, can actually operate in the lunar environment. And you're talking about a shit ton of material that is available to you in the form of everything from like the lunar ice caps on the moon to, regolith you can actually use to actually start to build, macro structures, whether in low Earth orbit, lunar orbit, or somewhere or cislunar or something like that. And so that then allows you to now build massive, sort of spaceships without having the penalty of having to send them from the surface of the Earth. And so, I think, you, even without the economic incentive for Mars, if you have the economic incentives on low Earth orbit and the moon, the Mars problem just becomes so much easier relative to today. Just sending stuff, it's heavy down here.
Plus, we have the atmosphere.
Yeah, I mean, atmosphere, gravity, big gravity well, lots of things. Earth is barely on the edge of you just get a little heavier and a little thicker atmosphere, and the rocket equation shifts from barely being able to get out to literally, chemical rocket engines not having enough propulsion to actually, get out of the atmosphere. I think people forget about this. I forget the exact number, but it's something on the order of if you increased Earth's mass by about 40% and increased basically the atmospheric density by about 40%, no chemical rocket engine that is available to humanity today would be able to escape orbit. Basically, you would need more fuel than basically how much fuel the engine can take. And so we are basically as difficult as it gets for what explosions can allow you to do.
Oh, that's crazy. Obviously, Varda is doing kind of pharma manufacturing. What's the next use case that would have kind of economics in space, outside kind of communication?
Yeah, I always like to think of these companies as sort of generations of companies that form the infrastructure that enables the next generation, right? If you look at the early days of the internet, companies like Amazon building out AWS in 2008 is ultimately what enabled the next generation of Uber, Airbnb, et cetera, so that rather than them having to build their own data centers, they can focus on, ride sharing of cars and, home sharing of, homes. And I kind of think of space the same way, where you had that first generation of companies like SpaceX, like Planet Labs, that built up the initial infrastructure, for the space economy, whether it be, sort of rockets or, more robust satellite supply chains. And then for a while, until those companies were successful, like I mentioned, in 2012 through 15, there was no interesting companies being founded because there just weren't other use cases that made any sense. If you look at Founders Fund, we basically invested a lot into aerospace from 2009 through 12, and then basically took almost a 10-year break. And a part of it was you just needed reusable rockets to then enable the second generation of companies. And similar to the first generation, I don't think there's an infinite set of use cases. I think there is this in-space manufacturing use case. I do think that there's this in-space, basically gas station servicing, repairs, taxiing, basically use case where now that you have a higher density of basically vehicles on the highway, you can now justify basically putting gas stations on the highway versus before you couldn't. And then I don't think there really is much else. I love that there's a lot of people working on a wide variety of other sort of commercial use cases, but I don't think anything else makes sense in today's generation. When those two business models succeed, whether it's in-space manufacturing and these in-space gas station servicing taxi systems, then I do think it then enables things like asteroid mining, lunar ice mining, et cetera. The way that I like to describe it is people always talk about wouldn't it be amazing if you took 10 tons of, ice from the moon and put it into low Earth orbit? And I always tell people, who's going to use that ice today? Even if you had an asteroid that you brought into low Earth orbit today, there's nobody up there that is built for or uses tons and tons of water on a daily basis other than the International Space Station. But if you have something like Varda succeeding, where you have a massive factory or you have a really large gas station that is consistently refueling satellites, that is an entity that would very happily buy, sort of lots and lots and tons of water. And so, I think right now there isn't really anything that interesting outside of basically those two, sort of in space. But in another 5-6 years, as things like Varda and these space gas stations succeed, I do think then there start to be more, sort of economic use cases that open up.
When you say space gas stations, do you literally mean like there's people sending gas to space and then distributing it within satellites that are already in space? That's actually a viable market?
Yeah. There's people actively working on this today that have contracts from Space Force, Air Force, NASA for initial sort of demonstration missions. Everything from refueling geostationary satellites to extending the lifetime of satellites that are in low Earth orbit. It's again, I think the easiest analogy to think about is just when there weren't that many cars on the highway, it was just easier for everybody to carry their own gas. Versus when there started to be lots of cars on the highway, it's a little easier for there to be a centralized gas station, and instead you just refill anytime you're kind of close to the gas station.
Apart from getting water from an asteroid or the moon, is there any other, I guess there's H3 mining on the moon. Are there other things that would be useful to have in low Earth orbit? Like steel or something?
Yeah, I mean, I think when you start to think about, helium-3 or like, platinum or things like that, those would then just be more like returning down to Earth. Obviously, hopefully we have like lots of nuclear reactors in space over time, but it's more likely that the helium-3 and platinum from an asteroid, more gets like returned down to Earth versus like used up in space, basically. So yeah, I think, outside of, those, then there's definitely more of a drop off, and it's kind of also probably hard to perfectly predict, sort of that far out. Then you start to probably get into the worlds of, what looks a little bit more like the, sort of United States colonies, where like the forward base on Mars ends up like discovering some sort of natural resource that Mars has, very, plentiful amounts of that, somewhere else in the solar system isn't. And so they end up sending back, sort of trade ships, back to Earth. But yeah, that stuff is like so fanciful that it's kind of hard to, perfectly predict. But surprisingly, there's not an infinite list of business models after the ones that I articulated, right? Like if you go from in-space manufacturing, there's for sure like tourism, hotels, etc. But, I don't find that to be like that interesting. You have the gas stations. You then have like, resource extraction for use in space, like, water, et cetera. Or you have resource extraction, for use on Earth, like helium-3. And then, beyond that, yeah, I'm not sure about that.
Do you think it'll always be extremely uncomfortable living in space? Or do you think over time we'll have artificial gravity and other things and it could be like pretty comfortable living there?
There'll be a 4 seasons in space at some point. It'll take some time, but for sure. I mean, there's no reason why you can't replicate all of the niceties that we have down here on Earth, basically in space, and get all the benefits of being in space. I definitely imagine a day where like rather than people coming to South Florida to retire, they instead go to the surface of the moon, given that you just have lower gravity, and so you can be more mobile, and so you might not be able to like run around and play golf in your full 18 holes if you're like 95 and bones are cracking a little bit down here on Earth, but you sure as hell can do it when like gravity's a lot less. And so yeah, I think if anything, there may be preferential comfort in space over time. It is not comfortable today, to be clear. Like if you read the twin study that they did with Mark Kelly and oh gosh, that's the senator and his brother. Anyways, his twin brother, I forget his twin's name. But anyways, the two twins basically went up to space. Mark, who went up for a year, man, if you read his book, his retelling of like the first like week when he was back after being up in space for a year is just brutal. Like it is, everything in his body was not working correctly when he was down here. And like it took like a long time to get back to normal.
All right. That's a good point to maybe come to a stop. Both the 4 seasons and the 1 week of pain. This is a super interesting chat, Delian. Thanks for taking the time.
It was great, Delian. We're cheering for you. You're building a great company.
Thanks, Raj. Thanks so much for having me, guys.
Raj, that was a super interesting conversation. What was your kind of favorite part?
Well, I did not expect that, honestly. Like I was looking at the website beforehand of Varda, and I was pretty confused, honestly. I didn't have no idea like what exactly they do. It sounded very like far-fetched, to be honest. I thought, well, there's a bunch of investors wasting money on this one.
Wow, you came in as a skeptic.
I came in as a skeptic, absolutely, yeah. And and Delian doesn't have a background either in like space or anything, so it's not like I come in as a fellow entrepreneur looking at it, and I'm like, geez, this seems a bit like science fiction type stuff. And we've seen a lot of companies out there who they just raise a bunch of money for something that sounds great that could be a decade out, and then they all eventually what happens like like a magic leap, right? They never make it past the chasm, right? And so I think being a skeptic is probably the default here, just based on the history. But I mean, Delian won me over. I mean, he knows his stuff. He knows the science inside out. He knows what he's working on. Like the application is very clear. The economics are very clear to him as well. And I came away thinking, well, this should happen. Like there's going to be a bunch of problems to solve, but everything he said made a lot of sense. And it seemed like he's picked the right narrow application for a startup to work on. What were your thoughts?
Yeah, the pharma thing is kind of interesting. In hindsight, it seems obvious, I guess, after that conversation that, hey, this is just the highest dollars per kilogram use case here. What's interesting is, I think, as a non-pharma person, I had no idea that the gravity of the conditions while like crystallization was happening can be a huge difference. I think it makes sense. I had always thought that the applications would be like carbon nanotubes or like something like that. So it's kind of interesting to go, hey, actually, there's just like simpler, like not future sci-fi kind of applications in space.
Yeah, it's for sure. I mean, it sounded like it was something that was well understood. They already did some testing in the ISS, and like
Yeah.
there were some promising early trials there. And the fact that they were able to launch something within 2.5 years of starting,
Yeah, that's crazy.
it's really promising. That's promising for the whole space ecosystem. Because I
Yeah.
think one thing that Starlink in particular is proving out is like there's like real applications in space that people maybe haven't thought of before or really haven't really invested in before, and so that probably allows for a lot more space companies to go out and try some new stuff.
Yeah. I also thought it was interesting that you hear about these experiments being done on the ISS, but you kind of just assume that nothing actually useful is coming out of it. But it actually sounds like basically the kind of research part and the science part of it was massively de-risked by kind of the work that the governments did in ISS. So, this could be a massive kind of dividend from that work.
Absolutely, yeah. And I think there's probably, you know the space better than I do, but there's probably a lot of interesting applications coming out of that. And it's great that that there's 1,000 flowers sort of blooming. Maybe not 1,000, maybe a dozen, but there's a lot of interesting stuff coming out of it. And I like the fact that it's really focused on a near-term goal and a clear ROI for a clear customer. So
Yeah.
that is really important.
One thing that was kind of funny to me is like kind of his initial thinking was like, how do we make a space civilization, right? How do we get humans on space? But the application is not very human intensive. And I actually think there's a reasonable likelihood that robots will get better faster than like the requirement, right? Like by 2029? There's a reasonable chance there'll be a reasonable humanoid robot that's got, enough articulation and enough kind of pre-programmed kind of AI skills that they can like basically do this manufacturing use case, right? Because we're already getting rid of humans in manufacturing on Earth. So it's kind of interesting kind of race that like we're trying to put humans in space, but then we're making robots that are good enough to do these things in the first place.
Yeah. I mean, for sure, there's going to need to be parallel track. I mean, you're right. The robotic manufacturing is much better now on Earth, but you're always going to need some human for like when the robots break, right? In general.
For now.
Yeah, for now. Yeah. So even probably the robot factories here have some level of humans in it. And he admitted the same. So, but yeah, humans are very expensive, right? And so there's so much work going on in like robotic aviation with drones and things like that. And autonomous vehicles. So it's all going to kind of come together. So it's exciting to see that, right?
There's a really good book called Case for Mars. And there's definitely like a separate kind of mindset, which is very much like, hey, we just need to get to Mars, which is like, the only place it makes sense to put humans for prolonged periods is Mars, because you've got the kind of the atmosphere protecting you from cosmic rays, and you've got all of these kind of other kind of built-in systems there that like humans kind of rely on, like gravity and all that kind of stuff. So I think at least Varda is much more in the camp of like, let's make low Earth orbit work, whereas this is other camp, which is like, let's skip a low Earth orbit and let's make Mars work. I think actually like if either of them work, it helps each other, which Delian made that point. But it's kind of interesting to see these kind of opposing kind of viewpoints.
What's the economic argument for Mars?
Honestly, it's much more of the almost like a land argument. Mars has as much land as the continents on Earth. So it's more of an argument of, okay, we have a massive landmass there and we should go make it work. And eventually we can. It's more of a colonial argument than like a purely economic argument, I would say.
Yeah, I can see that. Okay. Makes sense. Well, that was a lot of fun. Very dense conversation too, because he gave a lot of information in a short period of time. So it was fun to listen to him.